Alright, so we're looking at parametrics with the parabola and finding certain lines. We looked at the chord before, so now we're going to look at finding the tangents and the normals. So first of all, let's look at a tangent. So our standard parabola, x squared equals 4ay. We'll just pick a random point, we'll give it the parameter p, so 2ap, ap squared. So the question is, what is the equation of the tangent? Well, again, no different to what we've been doing before. If we want to find the equation of tangent, well, a tangent is a line, so we need a point. We've got that. We need a slope. Well, that's where we started using calculus to find the derivative. So we've got to find the derivative. Rearrange it, make y the subject. Y equals x squared on 4a. So I get x on 2a for my derivative. That's one way I could have done it. I could have taken advantage of implicit differentiation. So I could have said, well, hang on. Differentiate x squared, I'll get 2x. That'll equal, well, I can't differentiate 4ay with respect to x, but I can with respect to y. So differentiate that, I get 4a times the y dx. Rearrange that, again, I get x on 2a. So either way, I get my derivative. We want to know at the particular point when 2ap, ap squared. So when x equals 2ap, the derivative is p. So there's an interesting fact. What that's telling me is the slope of the tangent at any point is the same as the parameter. So whatever the parameter is, that'll be the slope of the tangent. Now it brings up another way I could have done it. I could have differentiated the parametrics itself. X is equal to 2at. Differentiate that with respect to t, I get 2a. Y is at squared. Differentiate that with respect to t, I get 2at. But then use my chain rule, bring it all together. I say, well, hang on, dy dx would be the same as dy dt times the t dx. And so I get t, the parameter. So again, it's showing that the derivative is equal to the parameter. However you choose to do it is up to you. The main thing we're interested in that the slope of the tangent's p. We have a point, we have a slope, so now I can put it into the point slope formula. Y minus ap squared. Now, which form did I put it in? General or y equals, or did I contradict? No, I've gone for y equals form. So y equals px minus ap squared. There's our general equation for a tangent to a parabola using parametrics. What about tangents from an external point? So let's draw a picture to describe this situation. Again, our standard parabola. You'll notice I've just made it 4y this time. So the focal length for this one, or a, is 1. So x squared equals 4y. If you've got an external point to a parabola, just like with the circle, you might remember the circle. You had an external point. You could always draw two tangents to the circle. Same thing's going to happen with our parabola. So I'm using the point 3, 2. There's one of the tangents. And of course, I don't know the equation of the tangent, so how do I know where it meets? I don't. So I'll just give it general equations. 2ap, ap squared, but in this case, a is equal to 1. So 2p, p squared. There would be another tangent that would meet at some other point. Let's give it the point 2q, q squared. Y equals x squared on 4. Dy dx is x on 2. What do you know? Slope of the tangent turned out to be p. Basically, I'm just doing the exact same thing again, except this time a is 1. Equation of the tangent, there it is, px minus p squared, same one that we just got. Well, that would be the equation of the tangent at p. What we do know is this. That tangent passes through the point 3, 2. So I now can substitute in and get the value of p. 2 is equal to 3p minus p squared. I get a quadratic which implies there's two values. And there are. Because one would end up being the value for p. The other would end up being the value for q because it meets the parabola at 2 points. Let's solve that. P minus 2, p minus 1. So p equals 1 or p equals 2. I can now substitute that back into my general equation of the tangent. And so I go, well, okay, one possibility there is y equals x minus 1. The other possible tangent is y equals 2x minus 4. So that's one where the information we know is actually a point not on the parabola. Another type of problem we like to do is find the points of intersection of two tangents. So again, let's draw the situation up. Gone back to x squared equals 4ay. 2ap, ap squared, there's one tangent. So I'm not going to do it a third time. We'd go and find the equation of the tangent. We've got our general one, y is px minus ap squared. 2aq, aq squared. Alright, so we know the tangent qx minus aq squared. Want to find the point of intersection of two lines? Solve them simultaneously. So let's call it T for tangents. I suppose y would be the logical one to eliminate. They're both negative. So get p minus qx is a p squared minus q squared. Difference of two squares on the right hand side. I can divide by p minus q because p minus q can't equal 0. Why? Right, if p minus q is equal to 0, then we'd be saying p equals q. Well, they would be the same point. So if they're the same point, how on earth would you get a point of intersection of two tangents? So it's okay, I can divide by p minus q. So the x coordinate will be whatever the focal length is, a times p plus q. Substitute back in, and we'll work out our y value. And, oh, that's interesting. Our point of intersection, the x value, is a times the sum of the parameters. The y value turns out to be a times the product of the parameters. So there's a nice neat little pattern there. So ap plus q, apq. Let's generalise the normal. Again, standard parabola. Randomise a point to ap squared, but this time the normal, which is at right angles to. Well, we have already worked out the slope of the tangent is p. Therefore, slope of the normal must be reciprocal and make it negative. So minus 1 on p is our slope for the normal. Let's put it in point slope form. Y minus ap will multiply by the p. X plus py is ap cubed plus 2ap. Let's find where those two lines intersect. If I was to draw two normals, it's another sort of point they might ask us to find. So we'll have our normal at p. Again, we'd show it's x plus py is ap cubed plus 2ap. A normal at q, well, don't have to derive the whole thing again, the only difference is the parameter. So it must have equation x plus qy is equal to aq cubed minus 2aq. Intersection, let's call it n for normals. Solve simultaneously. I think this time it's logical to eliminate the x's. P minus q, but once again I can divide by p minus q because p and q are different points. I've got a difference of two cubes there. So that's p minus q, p squared plus pq plus q squared, and then plus 2ap minus q, divide by the p minus q, look at that for a y value. A outside of p squared plus pq plus q squared plus 2. Sub back in, so x plus ap, the y value that we just found, is equal to ap cubed plus 2ap. Our x value minus apq p plus q. So there's one heck of a set of coordinates. Minus apq p plus q and a p squared plus pq plus q squared plus 2. It's probably a good reason why we don't bother memorising it. We just derive it when we need to use it. Alright, so we shall play with 9F.